Chicago Pile-1 was the world's first nuclear reactor to achieve criticality. Its construction was part of the Manhattan Project, the Allied effort to create atomic bombs during World War II. It was built by the Manhattan Project's metallurgical laboratory at the University of Chicago, under the west viewing stands of the original Stagg Field. The first man-made self-sustaining nuclear chain reaction was initiated in CP1 on 2 December 1942, under the supervision of Enrico Fermi, who described the apparatus as a crude pile of black bricks and wooden timbers. The reactor was assembled in November 1942, by a team that included Fermi, Leo Szilard, discoverer of the chain reaction, and Herbert L. Anderson, Walter Zinn, Martin D. Whitaker, and George Weil. It contained 45,000 graphite blocks weighing 400 short tons used as a neutron moderator, and was fueled by 6 short tons of uranium metal and 50 short tons of uranium oxide. In the pile, some of the free neutrons produced by the natural decay of uranium were absorbed by other uranium atoms, causing nuclear fission of those atoms, and the release of additional free neutrons. Unlike most subsequent nuclear reactors, it had no radiation shield or cooling system as it only operated at very low power. The shape of the pile was intended to be roughly spherical, but as work proceeded, Fermi calculated that critical mass could be achieved without finishing the entire pile as planned. In 1943, CP1 was moved to Redgate Woods, and reconfigured to become Chicago Pile-2. There, it was operated until 1954, when it was dismantled and buried. The stands at Stagg Field were demolished in August 1957, but the site is now a National Historic Landmark and a Chicago Landmark. Origins. The idea of chemical chain reactions was first put forth in 1913 by the German chemist Max Bodenstein for a situation in which two molecules react to form not just the molecules of the final reaction products, but also some unstable molecules which can further react with the parent molecules to cause more molecules to react. The concept of a nuclear chain reaction was first hypothesized by the Hungarian scientist Leo Szilard on 12 September 1933. Szilard realized that if a nuclear reaction produced neutrons or dinutrons, which then caused further nuclear reactions, the process might be self-perpetuating. Szilard proposed using mixtures of lighter known isotopes which produce neutrons in copious amounts. Although he did entertain the possibility of using uranium as a fuel, he filed a patent for his idea of a simple nuclear reactor the following year. The discovery of nuclear fission by German chemists Otto Hahn and Fritz Strassmann in 1938, followed by its theoretical explanation by Lise Meitner and Otto Frisch, opened up the possibility of creating a nuclear chain reaction with uranium or indium, but initial experiments were unsuccessful. In order for a chain reaction to occur, additional neutrons had to be emitted from fissioning uranium atoms. At Columbia University in New York, Enrico Fermi, John Dunning, Herbert L. Anderson, Eugene T. Booth, Norris Glasso, and Francis G. Slack conducted the first nuclear fission experiment in the United States on 25 January 1939. Subsequent work confirmed that fast neutrons were indeed produced by fission. Szilard obtained permission from the head of the physics department at Columbia, George B. Pegram, to use a laboratory for 3 months, and persuaded Walter Zinn to become his collaborator. They conducted a simple experiment on the 7th floor of Pupin Hall at Columbia, using a radium-beryllium source to bombard uranium with neutrons. They discovered significant neutron multiplication in natural uranium, proving that a chain reaction might be possible. Szilard suggested Fermi use carbon, in the form of graphite. He felt he would need about 50 tons of graphite and 5 tons of uranium. As a backup plan, Szilard also considered where he might find a few tons of heavy water. Deuterium would not absorb neutrons like ordinary hydrogen, and was a better moderator than carbon, but was difficult and expensive to produce. Fermi and Szilard still believed that enormous quantities of uranium would be required for an atomic bomb, and therefore concentrated on producing a controlled chain reaction. Fermi determined that a fissioning uranium atom produced 1.73 neutrons on average. It was enough, but a careful design was called for to minimize losses. Fermi and Szilard met with representatives of National Carbon Company, who manufactured the graphite, and Szilard made another important discovery. By quizzing them about impurities in the graphite, he found that it contained boron, a neutron absorber. He then had graphite manufacturers produce boron-free graphite. Had he not done so, they might have concluded, as the Germans did, that graphite was unsuitable for use as a neutron moderator. Government support. Szilard drafted a confidential letter to the President, Franklin D. Roosevelt, explaining the possibility of nuclear weapons, warning of a German nuclear weapon project, and encouraging the development of a program that could result in the creation. With the help of Eugene Wiener and Edward Teller, he approached his old friend and collaborator Albert Einstein in August 1939, and convinced him to sign the letter, lending his fame to the proposal. The Einstein-Szilard letter resulted in the establishment of research into nuclear fission by the U.S. government. An advisory committee on uranium was formed under Lyman J. Briggs, a scientist and the director of the National Bureau of Standards. Its first meeting on 21 October 1939 was attended by Szilard, Teller and Wiener, who persuaded the Army and Navy to provide $6,000 for Szilard to purchase supplies for experiments, in particular, more graphite. In April 1941, the National Defense Research Committee created a special project headed by physicist Arthur Compton, a Nobel Prize-winning professor at the University of Chicago, to report on the uranium program. Compton's report, submitted in May 1941, foresaw the prospects of developing radiological weapons, nuclear propulsion for ships, and nuclear weapons using uranium-235 or the recently discovered plutonium. In October he wrote another report on the practicality of an atomic bomb. For this report, he worked with Fermi on calculations of the critical mass of uranium-235. He also discussed the prospects for uranium enrichment with Harold Urey. Niels Bohr and John Wheeler had theorized that heavy isotopes with odd atomic numbers were fissile. If so, then plutonium-239 was likely to be. In May 1941, Emilio Segre and Glenn Seaborg at the University of California produced 28 micrograms of plutonium in the 60-inch cyclotron there, and found that it had 1.7 times the thermal neutron capture cross-section of uranium-235. At the time, only such minute quantities of plutonium-239 had been produced in cyclotrons, but it was not possible to produce a sufficiently large quantity that way. Compton discussed with Wiener how plutonium might be produced in a nuclear reactor, and with Robert Serber about how the plutonium produced in a reactor might be separated from uranium. His report, submitted in November, stated that a bomb was feasible. The final draft of Compton's November 1941 report made no mention of using plutonium, but after discussing the latest research with Ernest Lawrence, Compton became convinced that a plutonium bomb was also feasible. In December, Compton was placed in charge of the plutonium project. Its objectives were to produce reactors to convert uranium to plutonium, to find ways to chemically separate the plutonium from the uranium, and to design and build an atomic bomb. It fell to Compton to decide which of the different types of reactor designs that the scientists should pursue, even though a successful reactor had not yet been built. He proposed a schedule to achieve a controlled nuclear chain reaction by January 1943, and to have an atomic bomb by January 1945. Development. In a nuclear reactor, criticality is achieved when the rate of neutron production is equal to the rate of neutron losses, including both neutron absorption and neutron leakage. Thus, in the simplest case of a bare, homogeneous, steady-state nuclear reactor, the neutron leakage and neutron absorption must be equal to neutron production in order to reach criticality. The critical radius of an unreflected, homogeneous, spherical reactor was calculated to be, where m is the migration area and k is the medium neutron multiplication factor. The first generation of the reaction will produce k neutrons, the second will produce k2, the third k3, and so on. In order for a self-sustaining nuclear chain reaction to occur, k must be greater than 1. For a practical reactor configuration, it needs to be at least 3 or 4% more. Fermi christened his apparatus a pile. Emilio Segre later recalled that, "I thought for a while that this term was used to refer to a source of nuclear energy in analogy with Volta's use of the Italian term pile to denote his own great invention of a source of electrical energy. I was disillusioned by Fermi himself, who told me that he simply used the common English word pile as synonymous with heap. To my surprise, Fermi never seemed to have thought of the relationship between his pile and Volta's." Another grant, this time of $40,000, was obtained from the S1 Uranium Committee to purchase more materials, and in August 1941 Fermi began to plan for a new test. The pile he proposed to build was 8 feet long, 8 feet wide and 11 feet high. This was too large to fit in the Pupin physics laboratories. Fermi recalled that, "We went to Dean Pegram, who was then the man who could carry out magic around the university, and we explained to him that we needed a big room. He scouted around the campus and we went with him to dark corridors and under various heating pipes and so on, to visit possible sites for this experiment, and eventually a big room was discovered in Schermerhorn Hall." The pile was built in September 1941 from 4x4 by 12-inch graphite blocks and tin plate iron cans of uranium oxide. The cans were 8 by 8 by 8-inch cubes. When filled with uranium oxide, each weighed about 60 pounds. There were 288 cans in all, and each was surrounded by graphite blocks so the whole would form a lattice structure. The uranium oxide was heated to remove moisture, and packed into the cans while still hot on a shaken table. The cans were then soldered shut. For a workforce, Pegram secured the services of Columbia's football team. It was the custom at the time for football players to perform odd jobs around the university. They were able to manipulate the heavy cans with ease. The final result was a disappointing K of 0.87. Compton felt that having teams at Columbia University, Princeton University, the University of Chicago and the University of California was creating too much duplication and not enough collaboration, and he resolved to concentrate the work in one location. Nobody wanted to move, and everybody argued in favor of their own location. In January 1942, soon after the United States entered World War II, Compton decided on his own location, the University of Chicago, where he knew he had the unstinting support of university administration. Other factors in the decision were that scientists, technicians and facilities were more readily available in the Midwest, where war work had not yet taken him away, and Chicago's central location. In contrast, Columbia University was engaged in uranium enrichment efforts under Harold Urey and John Dunning, and was hesitant to add a third secret project. Before leaving for Chicago, Fermi's team made one last attempt to build a working pile at Columbia. Since the cans had absorbed neutrons, they were dispensed with. Instead, the uranium oxide, heated to 480 degrees Fahrenheit to dry it out, was pressed into cylindrical holes 3 inches long and 3 inches in diameter drilled into the graphite. The entire pile was then canned by soldering sheet metal around it, and the contents heated above the boiling point of water to remove moisture. The result was a K of 0.918. Choice of site. In Chicago, Samuel K. Allison had found a suitable space 60 feet long, 30 feet wide and 26 feet high, sunk slightly below ground level, in a space under the stands at Stagg Field, originally built as a rackets court. Stagg Field had been largely unused since the University of Chicago had given up playing American football in 1939. But the rackets courts under West Stands were still used for playing squash and handball. Leona Woods and Anthony L. Turkovich played squash there in 1940. Being intended for strenuous exercise, the area was unheated. The nearby North Stands had a pair of ice skating rinks on the ground floor, and although unrefrigerated, seldom melted in winter. Allison used the rackets court area to construct a 7-foot experimental pile before Fermi's group arrived in 1942. The United States Army Corps of Engineers assumed control of the nuclear weapons program in June 1942, and Compton's metallurgical laboratory became part of what came to be called the Manhattan Project. Brigadier General Leslie R. Groves, Jr., became director of the Manhattan Project on 23 September 1942. He visited the metallurgical laboratory for the first time on 5 October. Between 15 September and 15 November 1942, groups under Herbert Anderson and Walter Zinn constructed 16 experimental piles under the Stagg Field stands. Fermi designed a new pile, which would be spherical to maximize K, which was predicted to be around 1.04, thereby achieving criticality. Leona Woods completed her doctoral thesis and then was detailed to build boron trifluoride neutron detectors. She also helped Anderson locate the large number of 4x6-inch timbers required at lumber yards in Chicago's South Side. Shipments of high-purity graphite arrived, mainly from National Carbon, and high-purity uranium dioxide from Mallinckrodt in St. Louis, which was now producing 30 short tons a month. Metallic uranium also began arriving in larger quantities, the product of newly developed techniques. On 25 June, the Army and the Office of Scientific Research and Development had selected a site in the Argonne Forest near Chicago for a plutonium pilot plant. This became known as Site A. Some 1,025 acres were leased from Cook County in August. But by September it was apparent that the proposed facilities would be too extensive for the site, and it was decided to build the pilot plant elsewhere. While the subcritical piles posed little danger, Groves felt that it would be prudent to locate a critical pile, a fully functional nuclear reactor, at a more remote site. A building at Argonne to house Fermi's experimental pile was commenced, with its completion scheduled for 20 October. Due to industrial disputes, construction fell behind schedule, and it became clear the materials for Fermi's new pile would be on hand before the new structure was completed. In early November, Fermi came to Compton with a proposal to build the experimental pile under the stands at Stagg Field. The safety of building an operational reactor running at criticality in a populated area was a significant issue. However, the physics of the system suggested that the pile could be safely shut down even in the event of a runaway reaction. When a fuel atom undergoes fission, it releases neutrons that strike other fuel atoms and leads to the chain reaction. The time between absorbing the neutron and undergoing fission is measured in nanoseconds, often using a convenient unit for this purpose, the shake. Szilard had noted that this reaction leaves behind fission products that may also release neutrons, but do so over much longer time periods, from microseconds to as long as minutes. In a slow reaction like the one in a pile where the fission products build up, these neutrons account for about 3% of the total flux. Fermi argued that by using these delayed neutrons, and by carefully controlling the reaction rates as the power is ramped up, A pile can reach criticality at fission rates slightly below that of a chain reaction, relying solely on the prompt neutrons from the fission reactions. Since the rate of release of these neutrons depends on fission events taking place some time earlier, there is a delay between any power spikes and the later criticality event. If a neutron absorber, or neutron poison, is injected at any time during this period, the reactor will shut down. Compton felt this delay was enough to provide a critical margin of safety, and allowed Fermi to build Chicago Pile-1 at Stagg Field. There was a fear of a catastrophic nuclear meltdown blanketing one of the United States' major urban areas in radioactive fission products. Compton later explained that, as a responsible officer of the University of Chicago, according to every rule of organizational protocol, I should have taken the matter to my superior. But this would have been unfair. President Hutchins was in no position to make an independent judgment of the hazards involved. Based on considerations of the university's welfare, the only answer he could have given would have been no, and this answer would have been wrong. Compton informed Groves of his decision at the 14th of November meeting of the S1 Executive Committee. Although Groves had serious misgivings about the wisdom of Compton's suggestion, he did not interfere.